Okay, so we are reviewing the various properties we learned in Chapter 5. So here's a quick little screenshot of all the various things we looked at. So let's just take a quick little look at this, and then we'll go through a quick little PowerPoint that has some examples of these things and the decision-making tree to decide what formula is appropriate, in various situations. Okay, so we have empirical probability, we have classical probability. Those are the two that we really work with, right? Classical probability is used in cases where we know how many total possible outcomes there are, right? If you run into a situation and you don't know what the total number of possible outcomes are, then you can't use classical probability. Also, very important for classical probability, each of the possible outcomes must be equally likely of occurring. If you have a case where they're not equally likely of occurring, then you cannot use classical probability, right? So, for example, what is the probability that the Los Angeles Rams are going to win the Super Bowl this next season? Okay, we know how many possible outcomes there are, who's going to win the Super Bowl, because we know how many teams there are, right? But the odds are not equally likely of occurring. So we cannot use classical probability that way, right? On the other hand, if we had a 52-card deck and we're going to shuffle them all and randomly pick one card, okay, what's the probability that that one card is an ace? Okay, that is classical probability. There are 52 cards possible. They're all equally likely of occurring. That's something we can easily solve using classical probability. Right? Empirical probability is experimental probability. Empirical, experimental, same thing. Okay, so this means that we have a situation where we're going to repeat an experiment over and over and over and over and over many, many times. Ideally, thousands and thousands of times, if possible, right? We want to do it as much as is reasonable to do it. And what we're doing is we're keeping track of how often a particular event happens when we repeat the experiment. Right, so for example, if I wanted to know what is the probability that my car gets pooped on by birds. Lately it's been getting pooped on a lot by birds. So, I can just park it in the same spot every single day and just keep track of how many days, bird poop lands on my car. That's not something I can solve with classical probability. But if I do it for a long period of time, I always park my car in the same spot, and I do it for a long period of time and keep detailed logs of how often birds poop on my car, then I can get a sense of what's the probability that my car will get pooped on if I park it in that spot, right? Say if I leave it for 1,000 days, and out of the 1,000 days, 300 of those days resulted in bird poop on my car. So 300 out of 1,000, right? Which turns into about 30%. You would say that there's about a 30% chance that if I park my car there, bird poop will appear on it, right? So it's something where you can just repeat the experiment over and over and over and over again. Right now we're going through trials of various vaccines for COVID, right? So, what do? We give thousands of people this vaccine, and we wait several months and then come back and check to see how many of those people became sick during that period of time, right? So even with the vaccine, some people are going to get sick. Our hope is not necessarily, ideally it'd be great if the vaccine completely stops it and, you give it to 1,000 people and none of them get sick. That is a beautiful vaccine, but that's unrealistic. It reduces the number of people that get sick once they have the vaccine. So if we have 1,000 people and say we have two separate groups of 1,000 people each, right? 1,000 randomly selected people, we give them the vaccine. Another 1,000 randomly selected people, we give them a placebo, right? Just like a little sugar thing or something, so that neither group knows who actually got the vaccine and who didn't. And then we just watch them. And we keep track of them for 3 months, 4 months, 5 months. we come back and we retest everybody. And our hope is that the group that got the vaccine, that there's less people in there that got sick as compared to the group of people that didn't get the vaccine, right? I think a successful vaccine is about 50–60% effective. So that's really what we're hoping for, right? And then that little difference, just being 60% effective, is enough to help us curve down the growth of the virus through our population, right? So there's an example of another empirical probability. We can't solve that. We can't figure out how effective is a vaccine in any other way but to just do it, just repeat it over and over, give it to people, and see if we can detect a reduction in the number of people that receive or end up getting the virus. Any questions at all about the difference between empirical or classical? No? No? Sometimes we use computer models to recreate the experiment, right? Because it would be unrealistic, expensive, or just plain cruel to do it in real life. So, for example, if we design a new airplane, brand new design, and we want to see how aerodynamic it is and how it handles different stresses, things like that. The best way to proceed would be to create a very detailed computer model and then just repeat some sort of simulation over and over again and see how often the plane fails, right? The stress levels fail on the airplane. Once you get past the computer model, right? Maybe you create a computer model and it's really detailed in the computer model, and maybe you run an experiment 1,000,000 times, and out of 1,000,000 times, maybe 500 times it failed. That's pretty good, right? 1,000,000 times, only 500 times it failed. Maybe you're ready to move forward with the design. Maybe you start building parts of it. Maybe say the wing. Maybe you do you build one scale production model of the wing, and now you subject it to physical stresses. You put weight on it, you shake it, you strike lightning on it. Various things to see how it stands up to the stresses. And again, that would be experimental data, right? How often? What is the likelihood that this design will fail? Well, you just do a lot of experiments, keep track of your work, and then from that you can extract some sort of a probability. Good. That experimental probability, of course, is inferior to this, right? Because this is the exact probability. This is also called the theoretical probability, and the experimental probability is a little inferior because it might not give you the exact answer. It might give you the exact answer, but it might just give you something close to it, something hopefully good to a good approximation. But we never really know when we just have an experimental probability. We never really know how close to the real answer it really is. Right? We just gotta hope that the law of large numbers is working. That as we repeat the experiment over and over a large number of times, that the empirical probability will begin to approximate the classical probability. Good. Okay, so we covered quite a bit of that early on in Chapter 5. Are there any questions about these guys? So empirical, do a bunch of experiments, keep track of your results. That's how you can find the probabilities. Classical, know all the possible outcomes. All the possible outcomes must be equally likely of occurring. And then you can just count things, right? Remember the notation of this giant P represents the probability of, and then this guy in here is the event. So make sure you remember that for our exam. I want complete mathematical sentences. So probability of event, and then some sort of a fraction if it's a classical probability or a empirical probability. Remember this notation, capital N of, means the number of outcomes in this event. Good, good, good. Okay, then we covered the addition rule for events. So there were two rules. One of them is for disjoint events, and one of them is in general. Personally, I just like the general one since it covers everything, right? So this is a subcase of this, right? One particular case of this is this one. So I just think it's probably better to work with this one. So if we have a case where two events are disjoint, the probability of event E or event F is equal to the probability of E plus the probability of event F, right? So if they are disjoint, then we can just find the probability separately and add them. Good, good, good. If the events are not disjoint, so they fail to be mutually exclusive, there is some outcome that event E and event F share in common, then here is our formula for it, right? Okay, and then in the case where event E and event F are disjoint, we know that this probability is 0. So if this probability is 0, then it just reverts back to this one, right? Which is why I just prefer the general one. Okay, we talked about the complement rule before, right? Anytime you have some sort of an experiment and you lay out all possible outcomes, you can partition it, you can divide it into event E and not event E, right? Anytime you have any kind of a sample space, you can always divide it into the event and then not the event, right? Not the event is the complement of it. Good. And we know that the probability of the event plus the probability of not the event must be equal to 100%, or from there we can solve for either one, right? So again, we covered that in detail. Then we get to the multiplication rule for independent events, right? Two events are independent, then the probability of E and F is equal to their multiplication. Find the probabilities independently, multiply them together. And then that can be extended to multiple events, n number of events. Good. Next, we went to conditional probability, probability of event F given event E. And there was a couple of ways for you to kind of denote the same thing. So probability of E and F divided by the probability of E is one way to do that. Also, the number of outcomes in event E and F divided by the number of outcomes in event E, right? So these are equal signs. All three of these things mean the same thing. And then also, if we just multiply, take this guy right here, and we multiply both sides by P of E, probability of E, then we get to this statement. Probability of E and F is equal to probability of E times the probability of F given E. Good. So again, we covered this in a lot of detail. I think this is section 5.4. So this is a really hard one, section 5.4. So if you are having trouble, make sure you review that section and watch the videos, do the homework. Good. And then finally, this last section we covered, 5.5, introduced us to various counting techniques. So we introduced the factorial notation. We talked about combinations and permutations, right? So combinations of n choose r, permutations of n choose r, right? So permutations was the number of ways in which we can select r objects from n unique set of objects, right? So we have n in a pool, and we're going to pick r of them. And we care about order, the order in which they are selected. Good. So the classic question for this one is, 10 people are, 10 people enter a race, and we want to know how many ways are there for someone to come in first, second, or third place in that race. Well, order matters, and we're picking 3 out of the 10. So that's permutations of 10 choose 3. On the other hand, the other classic way for combinations of n choose r, here's our formula. We have 10 people in our pool, and from those we're going to pick 3 people to be in a committee, and we don't care about the order, right? So combinations are when we don't care about the order. We have a pool of unique people, and we're choosing them. We're not going to repeat the same person for a committee or for winning first, second, or third place. So repetition is not allowed. The people in the pool are all unique, and we're choosing r of them from a pool of n of them. Good. So order does not matter for combinations. Order does matter for permutations. So we'll look at some examples of those cases in a second as well. And finally, we had a weird little formula for permutations with non-distinct items, right? So how many ways are there to completely line up a set of values when some of them are identical, right? So this was like the example I had with markers. You know, we have like 12 markers, but 4 of them are yellow, 3 of them are orange, 2 of them are green. So some of them are identical. So as I decide different ways to line them up, sometimes you can detect that something has happened, right, based on the colors. So sometimes you can detect it, and sometimes you can't. So if I switch around 2 colors that are the same, you can't tell that I made a difference, right? So some of those count as one. So here is the formula for it. And again, we went through it just in the last couple of videos in section 5.5. So if you have more questions about that, you know, reference those videos or do those homework assignments. Any questions about any of these formulas in general? I'm about to go through a little slide thing, a little PowerPoint presentation on them as well. Any questions right now? No? No? Okay, let's go through the slide then and see how we do. Okay, so putting it all together, determine the appropriate probability rule to use, determine the appropriate counting techniques to use. Okay, so that's the objective of this section. So the author provided this really fantastic flow chart to kind of help guide us through the various formulas and the different situations we might face. Okay, so here's a little flow chart. So are you finding the probability of a single event? Is it a single event? Yes versus no. Okay, so if it's a single event, if you're over here, are the outcomes equally likely? Right? So for example, we're going to roll the dice, a pair of dice, one time, and we have some sort of an event we want to find. That's a one-time event. There are 2 events, so maybe we're going to roll a pair of dice and then we're going to pick a card from a 52 deck card, right? So then 2 events. So that's this first question. Single event versus not a single event. Good. Also, the events, it could be the case where we have the little ping pong balls, right? We looked at those examples. One experiment is going to happen, but there are people betting different things on it, right? Somebody thinks it's going to be either the number 1 or the number 7. Somebody else thinks it's the number 1 or the number 2 or the number 8, right? So there's different events that we're going to be including, right? So that would be a case for multiple events. Good. Okay, so if we have one single event, right? One ping pong ball is going to be selected, and we just want to know what's the probability that it's even. That's it, just one event. Okay, so now once we know it's one event, the next question is, are the outcomes equally likely of occurring, right? If they are equally likely of occurring, yes, then we have ourselves a case of classical probability. So the probability of the event, E, is equal to the number of outcomes in event E divided by the number of outcomes in our sample space. Good? So in the little ping pong ball, if there are 10 ping pong balls, and we want to find what's the probability that it's an even one, well, we count how many outcomes are evens and how many outcomes are possible, and then we divide them, right? Or maybe we're just getting one card out of a 52 deck card and we want to know, is it an ace? Okay, then that is one event. It's an ace when you pick out one card, yes. And the events are equally likely, I'm sorry, not the events, the cards, there are 52 cards, and out of the 52 cards, they're all equally likely of occurring. We're only picking one. So there are 4 aces out of 52. That would be our answer, right? Probability of an ace. Well, let me write that one down. So just sort of a classic example of this guy is the probability that we have an ace when one card is selected, and that's equal to the number of ways in which we can have an ace divided by the number of values in my sample space. Good. And there are, whoa, there are 4 aces in the deck out of 52 cards. So that division will tell me the result. Good. Okay, on the other hand, if they are not equally likely occurring, right? So maybe the question is, are the Rams going to win this year? Or maybe it's, you know, is it going to rain tomorrow? Or maybe it's, you know, Does a scratcher lottery ticket is a scratcher lottery ticket a winner? Right? You're at the table and there's those little roll packets. You take one out and you scratch it out. Is it a winning ticket? Okay, so if the outcomes are not equally likely of occurring, then we have ourselves. Is it possible to get empirical data? Can you repeat the experiment over and over and over again to see if we can figure out an empirical probability? If yes, then you have yourself your formula for empirical probabilities, the frequency of event E divided by the number of trials. On the other hand, if you cannot repeat the experiment over and over again, right, like are the Rams going to win the Super Bowl this next season? We can't possibly repeat that experiment, right? I mean, we can't create a computer model to completely recreate the entire season because there's just too many unknowns, right? We don't know, for example, injuries. I have no idea, if it's the beginning of the season right now, I have no idea how many players are going to stay healthy, for how long. There's so many variables that are going to happen that, I don't know. Weather is another thing. I don't know what the weather is going to be like, for the entire season. I don't know what the player injuries are going to be for the entire season. And, of course, choices that say, the coaches make. I don't know whether they're going to play a player or bench them, or maybe some player gets kicked out and, is penalized and can't play for 2 games, or, just so many things. There's no way a computer model could ever do it. So we're left with just the last thing, which is subjective probability. Subjective probability just means a professional tells us what their professional opinion is, and that's all we got. Okay? So far we're okay? If we do have multiple events, we go this way. Now we have the case of or, and, or at least. These are the 3 cases we kind of dealt with. So we have probability event E or A, the probability of event E and event A, or we have an at least situation. What's the probability that at least 7 phones are defective? What is the probability that at least 2 people survive the year? Right, so the words at least are in there. Good. So if we have an or statement, or is synonymous with addition, right? So if they are disjoint, we find those probabilities separately and add them. If they are not disjoint, then we have to think about the and statement. That's the probability that they both happen at the same time, and then we use the general rule for addition. On the other hand, if the probability involves an and statement, we want to know the probability of both, then we need to know whether they're independent or not independent. Good. And mutually exclusive, the question of whether 2 events are mutually exclusive versus whether they're independent, these are 2 separate questions. I think people mix them up a lot. So independent, remember our definition for independence means that if the probability of event E and event B are independent, if the occurrence of one event does not affect, in either way, positive or negatively, does not affect the probability of the other event, right? They're not impacted by each other. Good. So again, go back and look at that chapter. I think this was 5.3 if you want more clarity on that. Good. Okay, so if they are independent, we know that this is our rule for it. Probability of E and F is equal to probability times the probability of F. If they are not independent, then we got to use conditional probability, which is section 5.4, which is the probability of E and probability of F is equal to probability times the probability of E given F. Good. And then we had cases where we had this at least, right? And the probability of at least something happening is equal to 1 minus the probability that none of it happens. Good. So it's just a nice little shortcut that we use sometimes. Questions, 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 questions? Okay, so let's jump into some examples. We already did that. Now we already went through all that. Okay, so here's an example. Let's just jump into some examples. In the game show Deal or No Deal, a contestant is presented with 26 suitcases that contain amounts ranging from 1 penny to $1 million. The contestant must pick an initial case that is set aside as the game progresses. The amounts are randomly distributed among the suitcases prior to the game. Consider the following breakdown. So there are 8 suitcases that have between 1 penny and $100. There are 6 suitcases that contain between $200 and $1,000. There are 5 suitcases that contain between $5,000 and $50,000. And there are 7 suitcases that contain between $100,000 to $1 million. Okay, so those are the various suitcases. So there are a total of 26 suitcases. They're all randomly placed on the screen for the contestant to choose. So as they are choosing, they're randomly picking suitcases out of the 26, right? The probability of this event is not compound, right? Decide among the empirical, classical, or subjective approaches. Decide among the empirical, classical, or subjective approaches. Each prize amount is randomly assigned to one of the 26 suitcases, so the outcomes are equally likely. From the table, we see that 7 of these suitcases contain at least 100,000. Right, so here they are, 100,000 to 1 million. At least 100,000, so 100,000 to 1 million. That's 7 of those. So if we let the event E equal worth at least 100,000, then we can compute the probability of E that it's worth at least 100,000 using the classical approach. Right? So again, this notation, the probability of event E is equal to the number of outcomes of event E divided by the total number of outcomes in our sample space, of which there are 26. Right? So 7 out of 26, which divides into 0.269, which can be rewritten as 26.9%. Good. That reminds me, for the exam, people have this habit of rounding everything to a whole number. So make sure you get out of that habit. I don't want to see, if this was the question, I would accept this or I would accept that, but I don't want to see this as 27%. Okay, so don't, get out of the habit of automatically rounding everything to a whole number. At least 2 decimal places, usually 4 is good, but there will be instructions on the exam, so make sure you follow those instructions. Good. Okay, so now when we want to interpret it into language to interpret that percent, this is often a way to interpret that. So 26.9% means, a way to interpret that is that in 100 different games, we would expect about 27 games to result in a contestant choosing a suitcase worth at least 100,000. Right? That's what that means. The chances the contestant selects a suitcase worth at least 100,000 is 26.9%. That means that if we watch 100 different episodes of this game, we would expect about 27 of those episodes to be cases where the contestant chose a suitcase that was worth at least 100,000. Good. This is a randomly selected 100. It's not connected to percentages. It's just a way of expressing that. So you could just as easily multiply this number by any other number, 269. Say we choose 10,000. If we multiply 10,000 times this number, we get approximately 2,690. So another thing we could say is that in 10,000 games, instead of 100, say we watch 10,000 episodes, different games, we would expect about 2,690 of those episodes to result in the contestant choosing a suitcase worth at least 100,000. Good. So this 100 is arbitrary. 1,000 is another good choice as well. 10,000, 100,000. It's just a way of expressing, what it means for you to have a 26.9% probability of selecting a suitcase worth at least 100,000. Any questions? No. Okay, here's another example. According to a Harris poll in January 2008, 14% of adult Americans had 1 or more tattoos. 50% have pierced ears, and 65% of those with one or more tattoos also have pierced ears. What is the probability that a randomly selected adult American has one or more tattoos and pierced ears? Okay, so we have lots of numbers and lots of sentences running around here. This is a fantastic exam question. So let's kind of highlight the important things. For the purposes of this question, or at least for the purposes of the math, you know, the date is not important, right? It's important to keep track of it so that we know that this was based on information that came to us in January 2008. However, for the purposes of calculating the probability they asked us is not important. Neither is the fact that it's a Harris poll for the purposes of calculating an answer. Now, it is very important to consider that once we have a tabulated answer over here, to come back and think about the validity of the Harris poll. Do we trust them? Do they do a good job? Are they biased? You know, all those things, and you know, it's important to keep track of. But just for now, for the purposes of tabulating our answer here, let's ignore those things. Okay, now 14% of adult Americans have one or more tattoos, right? So that's one piece of information. Let's circle that. Well, I'll just highlight it. 14% of adult Americans have one or more tattoos. That's that. 50% have pierced ears. 50% have pierced ears. Okay. And 65% of those with one or more tattoos have pierced ears. So 65% of those pierced ears. Oh, I should probably have chosen a different color. Green, let's go back to blue. And 65% with one or more tattoos also have pierced ears. Okay, what is the probability that a randomly selected adult American has one or more tattoos and has pierced ears? Okay, so are these things independent, right? When we have an and statement, we want to ask ourselves, are they going to be independent? If one randomly selected person is chosen, is it possible that they have both tattoos and pierced ears? Yes, definitely. Does the probability of having one tattoo, does the probability of one event being true affect the probability of the other? Right? Like if I told you one randomly selected person is chosen, do they have a tattoo? You know, what's the probability that a randomly selected American has one or more tattoos? You know, think about what that is in your head. Now, if I give you additional information about that person, oh, by the way, they also have, this person has pierced ears, does that affect it, right? And it seems that it would be affected, right? If you're someone that is into getting tattoos, maybe you're more likely to be someone that's also into getting pierced ears, right? Or the other way around. So let's break this down into events. So the first one was this one. Let event E, well, let's call it A. Event A. Let event A be one or more tattoos. Adult American has one or more tattoos. Good. And so we know that the probability of event A is equal to 0.14, right? Just has one or more tattoos. Okay, has pierced ears. Let's call that event B. Event B is pierced ears. probability of B equals to 50%. Okay, so of those with one or more tattoos, so of those that have one or more tattoos, they also have pierced ears. So if we're just focusing on people that have tattoos, then we're looking at this. The probability that they have pierced ears given that they're of those people that happen to have one or more tattoos. Good. So in terms of our letters, this is the probability of B given A is equal to 0.65%. So let's read that again. And 65% of those with one or more tattoos, right, if we just focus on the people with tattoos, 65% of those people have pierced ears. So the question is, what is the probability that a randomly selected adult American has one or more tattoos? And pierced ears. Okay, so they want to know what's the probability that we have one or more tattoos and pierced ears. Right. So in terms of our letters here, this is probably an A and B. Good. And the probability of A and B, it comes in two flavors actually. We can either say that it's equal to the probability of A times the probability of B given A, right, this way, or another way to say this is that this is actually equal to the probability of B and A. Oops. So the order in which I write the and here doesn't matter. So one or more tattoos and pierced ears is the same thing as pierced ears and one or more tattoos. So that order does not matter, which means that I can also rewrite this as the probability of B times the probability of A given B. So there's two ways to write down that formula. However, if we go back and look at the information given, there's really only one way that we can answer this. Right? So they gave me probability of B and the probability of B given A. So this is my winner right here. This is going to be the probability of B, which was the pierced ears. So this is equal to 0.50 times the probability of, whoops, what did I do? A and B given. Oh, sorry. We don't want that. We want this one, right? We don't have this one. Probability of A given B, we don't have that. We have the probability of B given A. So we have this one actually. Good. So this is good, but we don't have this one. So instead, we want to use this one. They did give us the probability of A. That one was 0.14. And we have the probability of B given A, which is equal to 0.65. Good. So A was this one. It's the probability of having one or more tattoos times the probability of having pierced ears given that we have a person that has one or more tattoos. Good. So let me organize that a little bit more. Let's put it over here. So given all that, okay, so sort of scratch work of thinking my way through the various things, but now that I have exactly what I want, then I know that I don't necessarily need all of this down here. So when I'm ready to present this as my final answer, in fact, it turns out I don't even really need this part, right? This part is kind of extra. Probability that we have P or spheres is not needed for the purposes of this particular question, right? So we have sort of extra information there. It's just sort of designed to confuse you. Okay, so all we need is this over here. So probability that we have one or more tattoos, or more tattoos, and pierced ears is equal to the probability of one or more tattoos times the probability that we have pierced ears, given that we're only focusing on people that have one or more tattoos. Good. So using our notation, if we had let this be equal to event A and this be equal to event B, then we are saying that the probability of A and B is equal to the probability of A times the probability of B given A. Good. Good. Okay, so either way, we know that it must be the product of probability of A is 0.14 times the probability of B given A, the probability of pierced ears given that we're focusing on people that have one or more tattoos is 0.65. And if we multiply those two things together, 4 times 0.65, we get 0.91. 0.091, which then turns into 9.1%. Any questions? No? No. Let's see what the author did. Hopefully they agree with me. Yep, same thing. Probably E and F. So they just use different names for the events. Good. Okay, let's look at this example. The Hazelwood City Council consists of 5 men and 4 women. How many different subcommittees can be formed that consists of 3 men and 2 women? Okay, so we have 5 men and 4 women. How many different ways are there to form a committee that has 3 men and 2 women? Okay, so this is going to be a sequence of events to consider. So first we're going to select the men, then we're going to select the women. The order in which we pick them does not matter, right? So we're talking about combinations. Since the number of choices at each stage is independent of the previous choice, we use the multiplication rule and obtain the following. So the number of ways to pick total of 5, subcommittees. How many subcommittees? Total of 5 in a committee. Is going to be equal to the number of ways so that we can pick 3 men from 5 out of 5 men times the number of ways in which we can pick 2 women from the 4 women possible. Good. So this is going to be combinations of 5, choose 3. Out of the 5 men possible, choose 3 of them, right? Combinations of 5, choose 3. And once we get an answer to that, then we're going to multiply it by this. Combinations of 4, choose 2. Out of the 4 women, choose 2 of them. The order does not matter. And then when you're done with that, you multiply those 2 things together. Okay, so let's practice doing that. Clear. Okay, so we want 5 math combinations choose 3, that's 10, and then 4 math combinations choose 2, and that's 6. So we get a 10 and a 6. This is 10 times this is 6. There are 10 ways to choose 3 out of the 5 men, but the order does not matter. Again, you're not choosing the same person more than once. And so there's a total of 60 ways in which you can create this subcommittee of 5 people, where 3 are men and 2 are women, from an original pool of 9. Good? Good. What if we turn this into a probability? So that's not a question here, but let's find it. What is the probability that a committee of 5 is randomly chosen, is selected at random, this thing is here. Restate the whole thing. What is the probability? Find the probability that a subcommittee of 5 people consists of 3 men and 2 women if they are randomly selected from a pool of 9 people consisting of 5 men and 4 women. Right? So it's a very similar question. Before we were just asking how many ways are there to select this subcommittee, but now I'm asking what's the probability that this is the result. So if you're randomly selecting 5 people from this committee, what's that probability? Okay, so let event E equal committee has, let me check something. So this is event E is that the committee has 3 men, 2 women. Okay, so the probability that event E happens is equal to the number of ways in which event E can happen divided by the number of values in my sample space. Now we just talked about this. What's the probability that event E happens? Well, that's going to be the number of ways an event E happens. That's going to be the combination of 5, choose 3. Out of the 5 men, pick 3 of them, multiplied by the number of women, choose 2 of them. Right? So this will tell you, when we multiply them, that will tell you how many ways there are total. We said there were 60, 10 from here and 6 from there. And we divide that by the number of ways in which 5 people can be selected from the committee when you don't really care about gender. So if we just have a combination of 9 and we just choose 5, right? This tells you the number of ways in which 5 people can be selected from that 9 without caring about their gender, right? So this is the sample space, all possible ways to create a committee of 5 people, whereas this numerator specifically considers the cases where we have exactly 3 men and 2 women. Good. Good. Okay, so then this is going to be equal to 10 times 6. We know the numerator is going to be equal to 60. The denominator, well, let's just use our calculator. It's going to be 9, choose 5 combinations. So 9 math combinations, choose 5, 126. 126. So if we divide those two things together, we get 60 divided by 126. 60 divided by 126. And we get a 0.47619. So let's round that to 62. 4762. Questions? No. What if I wanted to find out what is the probability that there are, let's see, we're picking 5. Let's say I wanted to find out what's the probability that there are more women than men on this committee. Or the other way around. Yeah, let's do more men. Let's find the probability that there are more men than women in committee of 5. In committee of 5. Right? Okay, well that's going to break down into little subcases. You know, how can this happen? There are more men than women. Well, it could be the case that of the 5, there are 5 men and 0 women. That can happen. We were choosing from a pool of 5 men. Good. Or it could also be the case that there are 4 men and 1 woman. Good. Plus, okay, the case that there are 3 men and 2 women. Oops. Which we already considered. That was this case, right? Probability that we have 3 men and 2 women. Good. And then that's the only other case, right? Because if we move forward, then that would be 2 men and 3 women. So that would no longer be the case that there are more men than women, right? So these 3 events are disjoint. They cannot happen at the same time. If one committee is selected, either there are 5 men and 0 women, or there are 4 men and 1 woman. It cannot be the case that these 2 events happen at the same time, right? They're disjoint. So if I want to find the probabilities of this or this or this, I just have to find them independently and add them together. Good. And luckily we know the pattern already. It's a nice little pattern for each of these. This is going to be equal to the number of ways in which we can choose 5 out of 5 men times 0 out of the 4 women divided by number of combinations of 9 choose 5 plus this guy, which is the number of ways in which we can choose 4 out of the 5 men, times the number of ways in which we can choose 1 out of the 4 women, divided by 9 choose 5, plus this, which is the number of ways in which we can choose 3 out of the 5 men, times the number of ways in which we can choose 2 out of the 4 women, divided by 9 choose 5. Good. I gotta make a little bit of space here. Okay, so this guy is pretty easy. If we have 5 of them, how many ways are there to choose all 5? That's actually just going to be 1. There's only one way to do it. Pick them all. If we have 4 women to choose from and we want to pick none of them, how many ways are there to do that? There's only one way. Don't pick any of them, right? So this is really just 1 out of 1. And this guy we already know is 126. We already typed that into our calculator and we figured out that that was 126 ways to do that. Same with this, 126, and same with this, 126. We already calculated this from above. This was equal to 6. This was equal to 10. So we know that there's 60 in that numerator. And this is also an easy thing. If we have 4 women and we want to pick one of them, how many ways are there to do that? Well, there's 4 ways to do that, right? 4 women to choose from, pick one. How many ways can you select 1 out of 4? There's only one way. Now this one seems a little trickier, but it's not. If there are 5 people, 5 men, and we're going to pick 4 of them, how many ways are there to do that? That sounds confusing, but if you flip it around a little bit and think about the one person not selected, right? If you're picking 4 out of 5, that means one person is not selected. How many ways are there to leave one person out? There's 5 of them, so there's 5 ways to leave someone out. Okay, so some of these are pretty easy to figure out if you think through them. If not, you can just punch it into your calculator and get an answer. But then all of this then results in 1 out of 126 plus 5 times 4 out of 126 plus 10 times 6 out of 126, which then gives you 1 over 126 plus 20 over 126 plus 60 over 126, which then turns into 81 over 126, which then gives you 81 divided by 126, 6429, 0.6429, or about 64.29%. Okay, so the probability that there are more men than women on this committee is 64.29%. A pretty high likelihood, right? More than half. Good. Questions, 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 questions? And we saw the bulk of that was this case. So the most common thing that can happen in this scenario, right? If we focus on all the ways in which there could be more men than women, the most common scenario is going to be this one, that there are 3 men and 2 women. The second most likely outcome, given that we are focusing on the cases where there are more men than women, is this scenario where there are 4 men and 1 woman. And the least likely outcome within this scenario is that there are 5 men and 0 women. That's only 1 out of 26, which is a little unlikely. Okay? You have a committee of 9 people, 5 are men, you randomly pick 5, and it just so happens that you pick all 5 men. That seems a little unlikely. Any questions right now? No? No? No questions? No questions? No questions? Okay, keep going. Okay, so that's just showing that. That's just showing that. Uh-oh. I thought there was 4 women. Is this the wrong... 4 women? 4 women, 2 women. Yeah. How many different subcommittees can be formed consisting of 3 men and 2 women? How many consist of 3 men and 2 women? Independent, multiple choice counting, subcommittee, pick 2 women. Okay, yeah, so the author made a little mistake here. So what we did is right. Just going to move on then. Okay, how about this example? On February 17, 2008, the Daytona International Speedway hosted the 50th running of the Daytona 500. Touted by many to be the most anticipated event in racing history, the race carried a record purse of almost $18.7 million. With 43 drivers in the race, in how many different ways could the top four finishers, 1, 2, 3, and 4, occur? Okay, so we have a pool of 43 different drivers. All 43 of them could win number one, right? All 43 of them could be number 2 or number 3 or number 4, right? So we have a pool of 43. From those, we're going to choose 4 of them, and from those, the order matters. The same person can't be repeated, right? The same person, the same driver that wins second place can't also win fourth place. That makes no sense. So this is easy enough, I think, where we can just kind of do it the brute force method. So if we just think about how many ways are there for someone to come in first place, and then how many ways are there for someone to come in second place, and then in third place, and then in fourth place. Well, this is, how many ways can number 1 occur? There are 43 ways. 43 drivers can be number 1, assuming they were all, equally likely of occurring and all that. We're not taking into consideration who's a better driver and, who's more likely of winning, stuff like that. But we're just looking at we're not looking at probabilities right now. They're just asking us how many different ways can this occur. They're not asking you what is the likelihood that, a particular driver might win. Okay, so they all can be number 1. Some are more likely than others, but they're not asking us probabilities here. Okay, once somebody has chosen to go number 1, right? Once that number 1 place is taken, there are now 42 different drivers, right? There's 42 different ways in which number 2 can be placed. Once those 2 spots are taken, then we have 41 ways to select the third place. And once those 3 are taken, there are now only 40 ways in which the 4th spot can be taken. So this is an easy enough question to be able to answer it this way. And so we know that the number of ways to get a first, second, third, and fourth place is equal to 43 times 42 times 41 times 40. Multiply those 4 numbers together, and that'll be your answer. That's one way to do it. The other way to do it is just to implement our formula. This is definitely permutations, right? Permutations of 43 choose 4. Permutations of 43 choose 4 will give us the answer we're looking for, right? A total of 43 people. They're all unique. We're going to choose them one at a time to be first, second, third, fourth. We're never choosing the same person more than once. And the order matters. Good. So this is definitely permutations. And let's get our calculator out. Permutations, clear. So we have 43 math permutations. Permutations, enter. Choose 4. Enter. So that's a pretty big number. 29, 61, 84. So 2,961,840 ways that can happen, right? So if you're like a gambling man and you needed to put some money down on who's going to win first, second, third, and fourth, assuming that you just did it in a random way, just randomly threw out names out there of who's going to be first place, second, third, and fourth, you have 2,961,800 different ways in which the drivers can come in first, second, third, and fourth place. So that can give you a clue as to how to figure out the likelihood, the probabilities, assuming they're all equally likely, which they are not equally likely, right? This is clear. If this question was more specific about, Tom Jones is one of the drivers, what's the probability that Tom Jones wins first place? Well, I don't know. They're not equally likely of occurring. Some drivers are better than others, right? And some people have better pit crews, and some people have, just various little things that can give one driver an edge over another driver. So this is clearly not equally likely chances. Any questions? No? 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 Okay, so yep, that's exactly what the author did. Same thing. Moving on. Oh, that's it for this. Okay, let's try some of the example questions. So these are the exercise questions at the end of chapter 6. So let's just kind of go through a couple of these things. We won't have enough time to go through too many, but we can cover a couple. And of course, jump in if you have any suggestions on which ones we should do. These first ones I think are pretty easy, just pretty straightforward applications of these things. So let's see. Number 1, A, which among the following numbers could be the probability of an event? So we know that an event, a probability, must be a value between 0 and 1 inclusive of 0 or 1, but it cannot be bigger than 1, it cannot be lower than 0. So this is eliminated because it's a negative, and this one is eliminated because it's bigger than 1, right? So that's true. And then if we rewrite the probabilities in terms of a fraction, remember that a proper fraction is one where the numerator is equal to or smaller than the denominator. So this one's good. But if we have a case like this, is an improper fraction where the numerator is larger than the denominator, in a case like this, we convert it back to a decimal, we're going to get a value bigger than 1. Right? So this is not going to be a probability because it ends up being larger than 1. This is not a proper probability because it's a negative. Good. So this one's eliminated because it's negative. This one's eliminated because it's an improper fraction. Good, good, good. Okay, moving on down. Number 6, suppose that the probability of E equals to 0.76, the probability of F equals to 0.45, and the probability of E and F equals to 0.32. What is the probability of E or F? Okay, so when we want to have an OR statement, that's that's an addition rule. So it's going to be the general rule. It's going to be the probability of E plus the probability of F minus the probability of E and F, right? And we know we use that rule because they tell us that the probability of E and F is not 0. Good. So let me write that one down. So number 6 is the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. Good. And all those values are given, so that should be nice and easy. This is 0.76 plus the probability of F is 0.45 minus the probability of E and F, which is 0.32. Okay, so that little arithmetic should tell you the answer to number 6. Good. Okay, number 8, suppose events E and F are independent. In addition, probability of E is equal to 0.45, probability of F is equal to 0.2. What is the probability of E and F? Well, we know that if the two probabilities are independent, then the probability of E and F is equal to the multiplication of E and F. Good, number 8. Probability of E and F is equal to the probability of E times the probability of F, and that's because they're independent. And they're just given to you, so the probability of this one is 0.45, and the probability of this one is 0.2. So if we just multiply those two, we'll get our answer. Okay? Questions? Okay. Number 9, suppose the probability of E is 0.8, the probability of F is 0.5, And the probability of E and F is 0.24. Okay, are events E and F independent and why? Okay, well, we know the formula right here that works when they're independent, right? This formula is if they're independent. So just plug it in and see if they match. If it's true that 0.8 times 0.5 equals to 0.24, that means that this formula has worked and we're happy with that. On the other hand, if that's not true, if 0.8 times 0.5 does not equal to 0.24, which it doesn't, then that means that the two events are not independent, right? Because that formula didn't work. Good. Good. Okay. About number 11. Suppose the probability of E and F is equal to 0.35. The probability of F is 0.7. What is the probability of E given F? Okay, so for number 11, we want to take advantage of our conditional probability formula. Number 11, we have that the probability of E and F is equal to the probability of E. Oh no, well, we're working with F, so let's do that one. It's equal to the probability of F times the probability of E given F. Good. And now this part is given to us on number 11. They gave us this. This was 0.35. And they gave us the probability of F as 0.7. And this is what they're looking for, right? This is the question mark. So all we have to do is divide both sides here, and we should get that. Good. So 0.35 divided by 0.7 should be equal to the probability of E given F. Any questions? No? No questions, no questions, no questions. Okay. Okay, I think those are pretty easy. Let's pick a different, so 14, let's move on to a different one. So we only have a few minutes left, so let's pick something good. Number 16, gestation period versus weight. Preterm, term, postterm. Birth weights. Okay, so this looks to be birth weights of babies. We have a nice big table here where we have the preterm, so less than 1,000 grams, birth weights. So here are birth weights, less than 1,000 grams, between 1,000 and 1,999 grams, between 2,000 and 2,999 grams. Okay, so we have various weights of the babies. And then we have the numbers of babies that fall in those categories based on whether they went to term, post-term, and then preterm. Okay. All right, so we have a total of 3,948,828 babies in our table here. So part A, what is the probability that a randomly selected baby was born in 2018 was a post-term baby, right? So post-terms, here are the post-terms. There are 225,000 with 44, right? Post-term, they went past their due date. By a little bit, by some amount, which is a little less likely because I think that's an easier fix. Once you get to term, then I think that there are things you could do to make sure the baby arrives, on time, drugs and various exercises or various things. So I think it's a less likely or less common problem, right? A bigger problem is that they are born preterm. Period of gestation. Okay, so part A, is going to be the division of this divided by that, right? Post-term. So part A is going to be equal to probability of post-term is equal to a division of 225,044 divided by 3948828, right? All total 225,000 divided by the 3.9 million. Good. That division will give you the answer to part A. Okay, let's jump down here, see if there's anything more interesting. We have an OR statement. What is the probability that a randomly selected baby born in 2002 weighs between 3,000 to 3,999 grams? So that would be here. Or was a post-term. Or was a post-term. Okay, so if we kind of highlight everybody that qualifies under one statement, good. So these represent all the babies that were born with a weight of between 3,000 and 3,999. And then we can also focus on all the people that were post-term, all the babies that were post-term. So these babies, these babies, these babies, those babies, these babies, and these. Right? All of these were also post-term. So if I just add all of these numbers, all of them, that'll give me all the babies that qualify under one or the other statement. And then I divide that by my total number of babies, and that'll give me my answer. Okay, of course, that's a lot of writing, a lot of work. So we can come up with a shortcut. And the shortcut is going to involve recognizing that if I've already added all of these blue ones, that's these people. And I've already added all of the yellow highlighted, that's these people. So if I just add these two numbers, that's almost what I want, right? There's only one little hiccup, and that's that these people are part of these, and these babies are part of these, right? So these 160 have been counted twice if I just add these two numbers. So I'll have to remove them once. So this number plus this number minus that number will give me the answer I want. Good. Okay, let me write that down. So the probability that we have 3,000 to 3,999 or post-term that's going to be equal to 225,044 plus 2,596,802 divided, minus the overlap, minus 160,000 with 354. And all of that gets divided by the total, which was the 3,948 with 828. Good. So if we just get our trusty calculator, we end up with 225,049. Oops. 225,049 plus 25,96802 minus 160,354. So the numerator ends up being 266,1497. 1497 divided by the 3948828. And if we divide that, divided by the 3, 9, 4, 8, 8 to 8, I'm getting 0.6740, or about 67.4% chance that a baby randomly selected either weighs between 3,000 to 3,999 pounds or is a post-term baby. Any questions about how I got that from this table? Assuming that, I guess they're about right. Questions, 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 questions? No? Okay, that's good from there. And find another good one from over here. Illinois drawing, forming license plates. That's a good one. The license plate one. How about that one? Number 21. A license plate is designed so the first 2 characters are letters and the last 4 characters are digits, 0 through 9. How many different license plates can be formed, assuming that the letters and numbers can be used more than once? Okay, so we can repeat the same letters and then we can repeat the same numbers. And a license plate designed so that the first 2 characters are letters. Right, so number 21. We have, let's think about it in terms of spaces. 1, 2, 3, 4, 5. First 2 letters, and the last 4 are 4 characters or digits. So we have letters, this one and this one. I'll put it this way. Letters, and then numbers, and I need one more numbers, and you're allowed to repeat, right? A license plate is designed so that the first 2 characters are letters, and the last 4 are digits. How many different license plates can be formed, assuming that the letters and the numbers can be used more than once? Okay, so if we can repeat them, there are 26 letters. Right, and you're allowed to repeat it. So even though, let's say you chose the letter W, you can use W again. The license plate can start with WW. So there are still 26 options for the next one. Now the numbers, there are 10 characters, right? A base 10 number system means we have 10 unique little characters to indicate our numbers. So there are 10 options for that first space with a number. But since we're allowed to repeat them, there's still 10 for the next one, and there's still 10 for the next one, and there's still 10 for the one after that. Right? So a multiplication of 26 times 26 times 10 times 10 times 10. Right? So this is going to be our answer for number 21. Good, 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 good. On the other hand, if we are not allowed to repeat, right? Let's put it in a different color. If not allowed to repeat, then we'd have 26 options for the first spot. Once that first spot is taken, now the second spot, now there's only 25 options left. Good. For the numbers, that first spot there's 10 numbers available, but then you're not allowed to repeat, so now there's only 9 available for the one after that. And then there's only 8 available for the one after that, and then there's only 7 available for the one after that. So this multiplication would represent the result, the number of ways to create license plates if repetition is not allowed. Not allowed to repeat. Good. What if you're not allowed to repeat and all the numbers must be even? Let's put that in a different case. I'll put it in red, blue. Pick a different blue. Green, blue, purple, or purple. So now if not allowed to repeat, and numbers must be even. Even. Okay, so again, 26 for the first letter, then 25 for the next letter, and then, okay, so the numbers must be even, so there are 5 even numbers, right? The numbers 2, you write them down. There is the numbers 2, the number 4, the number 6, the number 8. Oh, wait a minute, there's only 4, right? Because I'm not using 10. 1 is not even, 0 is not even. So there's really only 4 characters, right? From this little pool of characters, 0 through 9, there's only 4 that are even. Okay? So there's only 4 ways to choose that first value. There are 4 ways to choose that first value. Once you've chosen that one, there's 3 ways to choose that one, then 2 ways to choose that one, and then there's only one final way over there to choose the last even number, right? So if they're all even numbers, you have to use the numbers 2, 4, 6, and 8 because you're not allowed to repeat. Good. What if you were allowed to repeat? So repeating was allowed, but you still keep this idea that the last even number, the last number must be even. Okay, so let's put as a last little space here. So let's say in this case, you are allowed to repeat, but the numbers must be even. Numbers. Let's stick with odd now. Numbers must be odd. Must be odd. Okay, so we have 1, 3, 5, 7, and 9. 1, 2, 3, 4, 5. 5 odd ones. Okay, but we are allowed to repeat. So the first space must be a letter. That's 26 options, but you're allowed to repeat. So now there's 26 options for that second space. Good. Now, odds. So there are 5 ways that we can choose that first odd number. Good. And then once that, well, since we're allowed to repeat, we can use the same odd number again. So there's 5 ways to choose the second one, and 5 ways to choose the next one, and 5 ways to choose the last one. So 26 times 26 times 5 times 5 times 5 times 5 would be the number of ways in which we can choose our license plate if repetition is allowed. Repetition is allowed. And the numbers must be odd. Okay, so I just added a few extra ones on there to that. Hopefully that makes sense. Let's just do a couple more. We're almost out of time. Any questions on anything? Okay, arranging flags. We've already done something like that. That's easy. I think we can do that. Because of a mistake, let's do number 26. Because of a mistake in the packaging, a case of 12 bottles of red wine contained 5 Merlot and 7 Cabernet, each without labels. All the bottles look alike and have an equal probability of being chosen. 3 bottles are randomly selected. What is the probability that all 3 are Merlot? Okay, so what do we got here? We got a pool of total of 12 bottles. 12 bottles total. This is number 26. 12 total. And from that 12, we have 5 that are Merlot. 5 are Merlot. And that means that 7 are Cabernet. Cabernet. Okay. And then they look identical. The labels are, it's all mislabeled. They look the same, the color's the same, the bottle looks the same. So when you randomly pick one from there, it's hard to tell which one's which. Okay, so we want to know what is the probability that when 3 of them are selected that all 3 are Merlots. So they didn't, you don't have any order or anything going on here. So we want to find the probability that we got 3 Merlots. And that's equal to the number of ways in which we can pick 3 Merlots, which means that by definition we pick 0 Cabernets. Out of all the number of ways in which we can pick any 3. Good. Order doesn't matter. The order in which we pick the 3 doesn't matter. So this is going to be combinations of 5 Merlots, choose 3, times combinations of 7 Cabernets, choose 0, divided by a total of 12 bottles, choose 3. Right? This represents the total number of ways in which you can choose any 3 bottles, any combination of any 3. Whereas this represents the number of ways in which we can pick 3 out of the 5 Merlots times the number of ways in which we can pick 0 out of the 7 Cabernets. Good. Okay, so 0 out of 7, we know that's an easy answer. That's just going to be 1. How many ways are there to not pick any of the Cabernets? There's only one way to do it. Just don't pick any. Right? Okay, the other 2 might require a little calculator work. So let's figure that out. That's going to be 5 math combinations, choose 3, which is 10. And then the other number, the denominator, is 12 math combinations, choose 3, is 220. Okay, 10 and then 220. So this is going to be equal to 10 times 1 over 220, or just 10 divided by 220. And then we can just divide those 2 numbers, and that'll give us our answer. 10 divided by 220. Good. So that's a pretty small number. It's 0 and then 45, 45. So this equals to 0.4545. Oh, there's an extra 0 in there. 0.4545. Good. So about 4.545%. Any questions? No? 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 What if, let's just play around with it. There aren't any subparts to this, are there? Oh yeah, there are. Part 2. What is the probability that exactly 2 are Merlot? Okay, 2 out of the 3. 2 Merlots. Whoa. So now we have the probability that we have exactly 2 Merlots. Well, that means that we have the number of ways in which we can pick 2 Merlots. And so by default, it must mean that we pick 1 Cabernet. Divided by the number of which in which we can pick any 3. Okay, so this must be combinations of, from the 5 Merlots, we're going to pick 2, times, and then from the 7 Cabernets, we pick 1 of them, divided by combinations of 12, choose 3. Good. Again, this one should be easy. How many ways are there to pick 1 out of the 7? Well, there's 7 ways. And this one, we'll just use our calculator. Combinations of 5, choose 2 combinations. So 5 math combinations, choose 2, enter. We get 10. Okay, so actually it's the same as this one. There's a symmetry that happens between the two. So that's 10. So this will be equal to 10 times 7 divided by 220, which gives you 70 out of 220. And so 70 divided by 220, 3182. Or approximately 31.82%. Good. Okay. What is the probability that none is a Merlot? Well, none is a Merlot is the same thing as saying we want all Cabernets. So it's just the probability of picking 3 Cabernets. Okay? That should be following the pattern, same thing, pretty easy. 0 Merlots, 3 Cabernets. So it'll be combinations of 5 choose 0, and then times combinations of 7 choose 3. Right? Divided by the same combinations of 12 choose 3. But that should be pretty easy. And then that takes us to this. Does anybody see any questions that they think are worth looking at before we sign off?